Right, well, hello everyone. As Martin said, I've come in as Plan B, so I didn't have as much time as I would have liked to prepare this, but it does cover some background to statistical analysis for planning and evaluation of inspections. And I think I should just clarify that the focus is on sampling. So I was very happy to be brought in at the last minute, though, because it gave me an opportunity to talk after John's talk, and John has been a great supporter of statistical analysis, particularly in the early days of the HOIS program when we were developing the statistical analysis recommended practice. And also Siga, who's chairing the session today, has been actively involved in HOIS work and statistics and other activities. So that they both what I would call early adopters of some of the methods and so on that we're going to be talking about today, and promoters of the whole approach. So, well, that didn't work. So just in the context of the HOIS digitalization activity, ultimately what it's about, like Siga was saying in the beginning, is really improving efficiencies, making better use of data, taking advantage of technology improvements as they're occurring very rapidly now. And one way to look at that is you can look at it across the different stages of the sort of integrity cycle, which I've put down in this context, going from assessment and planning, data collection, data analysis, and then update actions, which not everyone would necessarily see it in that context, but you can break it down in that way, and it's a way that highlights the role of technology and methods supporting improvements in these approaches and increasing efficiency, taking advantage of technology that is becoming very widely available and isn't, rapidly expanding in its capabilities along the lines of what John was talking about a short while ago. So this is just background context, and when you go through this in detail, which I won't now, but you'll see that there's many aspects of this where statistical analysis and statistical methods are fundamental to the applications. So I won't spend much time on this slide, but obviously there's a wide range of statistical applications in inspection and integrity, ranging from literally right at the very front end of the process to do with statistical signal processing. Much of what we do in risk-based inspection has at its core statistical philosophy, same with reliability, and then you can get into more detailed things around corrosion growth modeling, so not just looking at data from corrosion, but the models themselves are statistical phenomenological models increasingly. And there's, as I say, there's a wide range of applications. What I'm going to be really focusing on today is sampling inspections, where essentially what you're trying to do is deal with situations where there's some benefit to a partial coverage inspection. So that might be driven by a reduction in time and cost, or in some cases partial coverage may be the only option where you simply can't get to certain parts of a system. It's also worth saying that although there's growing interest in partial coverage inspection and use of statistics in that context, the approach is not something new. I mean, pipework inspection, for instance, or piping inspection has historically been based on very small coverage throughout a system. Things like storage tank wall inspections, those have also had very, very low coverage, typically historically. Ship hull inspections, that's another good example. It's been around for a long time with quite low coverage. So there was some interruption in the sound. Even though using those methods, there wasn't any formal statistical analysis, there was the implicit assumption that the data collected will be indicative of the condition overall. But the advances really in inspection technology, which give you large quantitative data sets, and statistical methods have driven application of formal statistical methods to support that sampling. So really trying to understand what is happening in the areas that you haven't inspected. So you take some sample coverage and use the data from that sample coverage to make estimates for the area not inspected. So the main principles, or your sort of basic assumption is that the corrosion present follows some sort of statistical distribution whose key characteristics can be described by a small number of parameters. So that requirement, as it turns out, is more often than not in place for typical in-service damage. And if you think about it, it's not entirely surprising, because corrosion is a natural process, and like many other natural processes, it often conforms to one of a small number of distribution types, which are typically associated with natural phenomena. And we're talking about a very wide range of things there, like, you know, what's the amount of rainfall, for instance, through to chemical reaction rates. These things are all typically associated with some sort of statistical behavior and regular statistical behavior. So the basic approach is to sample as in measure the variable of interest. And in the case of inspection, we're talking typically about, when you look at corrosion, we're talking typically about wall thickness or depth measurements, and those measurements are taken over defined areas, and we would typically be aiming to achieve a certain coverage or total number of locations. And then with that data, we identify, if we can, the applicable statistical distribution, and we establish the parameters for that distribution by distribution fitting, and then we use those parameters to make estimates. And in our case, often those estimates will be around minimum thickness. And it's worth recognizing that that's a little bit different than what a lot of statistical analysis or inferences applied to, is where you're actually trying to estimate what's the average behavior. We trying to estimate what's the more kind of extreme behavior, and that does introduce some additional challenges compared to the bulk of statistical methods, let's say. So the main requirements to apply it is that the behavior should be statistically consistent and conform to distribution. The region inspected should be representative of the overall area, so you need some level of homogeneity, and the sample size should be sufficient. So you need to have a sufficient amount of information. So looking at how inspection technology has changed the approach to statistical analysis, one of the big changes, I guess, over the last 20 years really has been the greater access to large volume data sets, typically in the form of corrosion mapping, where you'll be getting tens of thousands or up to tens or hundreds of millions of individual measurement points within an inspection. And that gives you a basis for doing much more detailed statistical analysis. So the basis for much of that analysis is, and this was all covered in the Hoyce recommended practice for statistical analysis, is essentially developing wall thickness distributions, where this is shown as a cumulative distribution, and you're plotting the proportion of area below a certain thickness. So you can see here the majority of the material is this blue color, which occupies the upper, bear in mind this is a log scale, that's sort of around 25% level. So most of this material, 75% of it approximately, doesn't have any corrosion, and that's represented by this part of the curve. Then you get this transition to the tail, which represents the corrosion, and this is the part of the curve that you are interested in. And obviously, as you go down through the colors, there's a smaller and smaller area associated with that. So a fairly tiny proportion of the area is at the sort of red color as such. Something like 10%, 10 to the minus 5 of the total area. So that's really the basis for, or what corrosion mapping type data or other quantitative data like laser scans for external corrosion provides you. So the wall thickness distributions give you a useful visualization of the characteristics of corrosion over and above what you would get from your typical colorgraphic corrosion map. I mean, obviously the corrosion map tells you a lot about the nature of the corrosion and so on, but it doesn't tell the whole story when it comes to things like, well, what is the proportion of area affected by corrosion? And the wall thickness distribution, where you get this transition point, very clearly indicates what proportion of area is affected by corrosion. And in this particular case, that transition occurs at about 10% of the area, so 10 to the minus 1. It also tells you about the nature of the corrosion, the tail behavior, the shape of that tells you something about the kind of distribution that's active. And it can also tell you about the nature of how that corrosion has grown in terms of do the areas which are deepest to start with continue to grow at the highest rate, and so on. And another piece of information that's useful is it tells you about the variability in the as-built thickness. So if you didn't have any corrosion, typically it follows a normal distribution, which would be indicated by this red curve, and the width of that, if you like, tells you about the sort of as-built variability or variation in thickness. And then finally, from our point of view, in terms of using that data, the distribution associated with the tail provides the basis for making estimates for the areas not inspected. So just briefly how that's typically done, and this is an example from the recommended practice training notes from the hoist document. So essentially this is data which follows an exponential distribution, so it's linear on this log scale, and in order to estimate the minimum thickness overall, we essentially extrapolate down from the level at which we have data, which is 10 to the minus 5. And if we had 10% coverage here, effectively we've got 1/10 of the area, so we want to extrapolate by a factor of 10. So we're going to take it down to 10 to the minus 6. So, I mean, in the case of an exponential distribution, it's a fairly simple curve fitting exercise, and you can make an estimate for that's your most likely minimum for the remaining 90% of the area that we haven't inspected. There's obviously a lot more detail to how you do those calculations than what I'm necessarily showing here, but that's the basic principle of extrapolation. So that gave you an overview of using wall thickness distributions. Obviously, many of you would be more familiar perhaps with extreme value analysis, which has been around for longer and as a stronger theoretical foundation when it comes to corrosion and many other applications. And there's been applications since really the 1950s in terms of not just inspection and integrity, but quite widely outside of that. The main applications for EVA within inspection and integrity really began in the 1990s, mainly with work coming out of Japan. And it's been used, sort of on and off since then. So it does predate the use of wall thickness distributions. Historically, where it's been useful is for data sets which are limited. So, for example, manual scanning over grids, where you're getting just a set of minimums. It does remain applicable to high volume data sets. You can still use it with corrosion mapping data, for instance. And the difference is that rather than using your full data set, like using the wall thickness distribution, you're basically using the extremes within blocks of data. So you break your data down into blocks typically, and then take the extremes, which would be for each block, either the minimum if it was you're looking at thickness, or the maximum if you're looking at wall loss. So by comparison to using the full distribution, you're effectively using a subset of that, and there are specific distribution types with particular characteristic called extreme value distributions, which would then be applicable to those arising distributions. And you then make the estimates by extrapolation of the extreme value distribution. So just to compare the two, the wall thickness distribution has really been, ease of use, let's say, has been facilitated by advances in inspection technology. You're retaining the full information for the area inspected. That extra data basically allows you to do more comprehensive sensitivity studies. It does reduce the uncertainty, typically, as would be linked to the sample size, which can be significant for extreme value analysis. The basis for the approach has been defined in detail in the Hoist recommended practice for statistical analysis, and it's been widely used. It has a number of other advantages, like giving you a basis for systematic measurement error correction, and the approach, as I mentioned, has been widely used, particularly for pressure vessel non-intrusive inspection. And I think it's generally preferred where the data is available and suitable. And when I say the data is available, you've got reasonably high density corrosion mapping data. So extreme value analysis obviously has the benefit of greater maturity of application. It's not reliant on high volume data sets where essentially now you're only looking at the extremes, and that does potentially give you some lower cost of inspection. It does lose information because you're only working with the extremes. The distribution can also be contaminated with uncorroded material. So if you've got grids or blocks of data where you don't have any actual corrosion, those can cause issues with the overall distribution that you're fitting. And there is a tendency towards greater uncertainty and sample size sensitivity. So there are, I think, significant benefits to using the full distribution as a basis for analysis, and I would certainly recommend that as a sort of default approach when you have got high volume data available. But it's also important to recognize that there are some exceptions, and the kind of exceptions would be where cost or availability of inspection delivering that high volume data is a constraint. So you may just have manual UT available on site, or you may be working with historical data where you don't have any high volume data. There are also situations where your high volume data has limited quality and reliability. So the surface condition, for instance, might drive noise, high levels of noise. You may have issues with your automated analysis where you're getting high proportion of spurious data. You may need manual intervention in any case to identify the minima. But some of these issues, I think, will start to be negated, I guess, when we start to see more machine learning type applications for ultrasonic inspection data, which is still an evolving field. I don't think as far advanced as what the kind of applications with the visual data that John was talking about. There may also be cases where you've got complicating factors in the data set. You're relying on manual data analysis, and the inspection equipment might not be configured to output those high volume thickness data sets. And I think that's still the case with some heat exchanger tube inspection applications, for instance. So if we look at with any of these methods, if there's a range of factors you should look at in affecting the estimates, and in terms of uncertainty, does the distribution fit the data that you have? How have you fitted the distribution? The mathematics of that is actually quite important. There's different methods of fitting distributions that are applicable in different cases. The selection can affect the results, as in where did you take your data set from, how big was your sample size, variation in terms of is the corrosion behavior homogeneous within the areas that you selected, and then measurement error also plays a role. It's important to say that the uncertainty tends to grow with the extent of extrapolation. So the lower your coverage is, typically the greater the uncertainty will be. Obviously with some caveats around that, but it is important to understand the contributors to uncertainty when you're making these estimates. So the next couple of slides, I wanted to just talk about an important issue that's sometimes overlooked when it comes to analysis of, or statistical analysis of corrosion data, and that's to do with the spatial characteristics. And the statistical analysis RP does highlight this, the importance of what's referred to in that document as density and homogeneity. And the density you can look at from the point of view of either the number of corrosion features per unit area. So how many dense corrosion would be where you've got a lot of corrosion features within a unit area. Otherwise, it may be sparse where you've got very few. Another way of looking at that is what's the proportion of area affected by corrosion. So if you recall the wall thickness distributions, that gives you the proportion of area affected by corrosion. A low density case would be where that proportion is very low. And why the density is important is it affects the amount of information available in a given sample size, as in the area or the number of locations as well that you've actually inspected. A low density means in order to collect the same amount of information, you would typically need a bigger coverage. And then another issue is homogeneity, and this really refers to how much does the behavior change over an area. And this graphic really is from, again, this is from the training notes for the HOIS recommended practice. This just tries to illustrate that, and essentially what it is if we're looking here at the scale of homogeneity. So at what scale do we need to look at things in order to get the same kind of picture as we would as any other area of that scale? Clearly at this very small scale, A and B, C and D, they actually all look very different. It's very easy to see that. Even if we increase that by a significant factor here to the size of E, F and G, you can still see there's some significant variations in terms of what we're seeing in each of those images. So here, in order to really be representative, we'd have to increase, probably at the level of maybe a quarter or a sixth of a third of this, a sixth of this area. We would start to see consistency in terms of the homogeneity. And it's important that the planning and evaluation actually considers both of these. And that is actually covered in the Hoist recommended practice for non-intrusive inspection, which makes specific reference to density and homogeneity, and also provides some, in the guidance notes, provides some guidance on how to assess upfront what your density and homogeneity may be. I won't spend too long on this slide, but essentially one way of assessing density and homogeneity and what's the impact on your results is to use subsampling. So again, these slides are from the training notes for the Hoist recommended practice, basically which goes through the details of how you would go about taking subsamples to assess sensitivity. So in terms of planning for inspections, there's obviously coverage is a key consideration. We're doing a partial coverage inspection, but how much coverage do we need? And perhaps also where do we need to cover? So the density and homogeneity, as I've just mentioned, are key considerations here. When you've got a lower density, you would need higher coverage, and lower homogeneity would also lead you to higher coverage. So just to illustrate that on this area on the left here, this is a very high density of corrosion, so we can get away with a fairly small coverage here and get the same amount of information that we would only get with a very high coverage, in this case of low density of corrosion. The distribution of coverage is also important. Generally, you prefer to have more smaller locations that are widely distributed, so not just putting all your coverage in one corner of an item, for instance, but distributing that widely across the item. And obviously, you have to consider practical and economic factors. Things like access. Can you actually easily get to certain areas? What's the surface condition like? Which for older assets is often a major issue. And what's the cost and time of a given inspection? So the other aspect that affects or should be considered at the planning stage is the measurement, and measurement accuracy is an important factor, because measurement error adds noise to the data used in the statistical analysis and tends to stretch out the distributions, and it basically contributes to uncertainty, making for less reliable estimates. So there is a trade-off between coverage, as in your sample size, and accuracy, and improving accuracy can support a reduction in coverage. Obviously, you have to still appropriately distribute that coverage. And what you can do trade-off studies based on simulation at the planning stage. So just a few examples of applications. Non-intrusive inspection I mentioned. So within Hoist RP103, it covers a process for implementation of NI. So starting with an assessment phase where you basically look at, is NI suitable and what are the requirements for NI in terms of coverage and so on. Then putting those requirements into a work scope, carrying out the inspection to that work scope, and carrying out the evaluation. So in terms of statistical input to this, it's at the assessment stage, defining what you need for the work scope in terms of coverage, and also at the evaluation stage. And sampling inspection, as many of you will know, is an important element of both type A and type B strategies within Hoist RP103. And for the type B strategy, which certainly for upstream is the majority of applications at present, the aim is to specifically permit a partial coverage inspection, and it is explicitly reliant then on statistical analysis to make estimates for the area not inspected, and that's covered in some detail in the recommended practice. So the approach basically is to carry out the assessment and planning stage where the coverage and performance requirements have a link back to statistical considerations, carry out the inspection, and then do the evaluation, which looks at conformance plus also a statistical analysis estimate element where you're estimating minimums for the uninspected area, and also looking at things like what's the probability that the minimum might be below some limiting condition, and also an assessment of measurement performance. So another application for statistical analysis using distributions is on corrosion growth rates. So this slide basically shows the kind of process where you have several repeat inspections. For instance, one way of estimating a corrosion growth rate is to go to the minimum thickness within all of your inspection and determine the minimum at each one of these 4 inspections, and then look at the change in that minimum. But that becomes quite prone to both random and systematic measurement error. And if you're trying to accurately establish corrosion rates, that you can end up being very sensitive to measurement error. If you take the wall thickness distributions for those subsequent inspections and align the uncorroded material, because you know the uncorroded material hasn't changed in thickness, so that gives you a reference to eliminate your systematic error, and then plot those distributions overlaid as we have here. The changes in the tail of the distribution basically give you an indication in the reductions in wall thickness over time, and this can be extremely sensitive because it is less sensitive itself to measurement error. So you can have a reliability of your corrosion rates which is very insensitive to your measurement error, your random measurement error. I think I'll move on. So just looking at some additional applications and status, additional applications would be things like restricted access inspection, piping inspection, optimization, and those of you familiar with hoist will be aware of the hoist guidance for effective pipework inspection from several years ago, and that's based on a number of different statistical approaches and methods of visualization. Storage tank wall and floor inspection, heat exchanger tube inspection. At the last hoist digitalization forum, Ricardo Gonzalez included an example of heat exchanger tube inspection. So it is something that's gaining momentum within operators. Compliance inspection, unpiggable pipelines. There's actually some PRCI guidelines in place for using extreme value analysis as a basis for planning and evaluation of unpiggable pipeline inspections. Martin, how much time have I got left?
I was on mute. I'll mute myself. 10 minutes left.
Okay, thank you.
I'll
finish up shortly. Thanks. So, looking at the benefits of statistical analysis, particularly the sampling approach, you can get more cost-effective inspection. You can better understand the condition of assets. You can improved understanding of uncertainty associated with that, and these things really lead to more effective integrity decision-making from both a risk and a cost perspective. You can get increased opportunities for use of NI in place of internal visual, reducing shutdown time, increasing production uptime, and also using this as a basis for QA for control of inspection service provider delivery. Just in terms of, I guess, the sort of status and way forward, the methods have been used by innovators and early adopters, both on the operators and service companies, but not yet fully utilized as routine, I think is fair to say. So there is substantial potential for increased application. And there has been a big increase in interest over the past several years, particularly with things like the Hoist digitalization project and many other initiatives across industry. There's a greater interest in using data better because we're also getting access to much more data. But even so, there are some restraints to be overcome. And one of the big restraints is resistance to change from an existing and integrity and inspection practice. There's also a question around confidence in new methods. So many people have adopted a sort of wait and see position. There's a cost of updating practice. And to some extent, some of these things are reliant on skills which are not currently widely available. So the solutions to this, I guess, lie in one of them being the integrity and inspection teams should include data science as a discipline, and it's really encouraging to see that that's starting to happen more widely, not just in the operators, but also in service companies. Importantly, also training in methods and applications. Obviously, that's needed for existing practitioners and is essential to adoption. Developing best practice is also important, and that's been a big part of the Hoist kind of activity, and is still part of that activity through the digitalization project. Also, greater automation, simplifying some of these processes, and there's a lot of potential for support from machine learning that will drive wider adoption. Having software tools accessible to integrity and inspection practitioners is also important to this, making it easier to actually carry out planning and analysis. And then obviously, as there's expanding experience, it'll lead to increased confidence. I think Siga mentioned the Hoist guidelines on information flow, and that kind of thing is really essential to kind of greasing the wheels of this process, I think, where it's part around greater automation, but just making the data easier to use and accessible. And that's not a given with many of the kind of processes as they exist now. So there is definite change needed and guidelines needed around how to make that change. So just to finish off then, back to where we kind of started around transformation of inspection and integrity, and hopefully this presentation, even though it's just focused on the sort of sampling applications, will give you a bit more insight into how some aspects of statistical analysis can help facilitate elements of this transformation. So that brings to the end my presentation, and thanks to Hoist members who've contributed to some of the projects we talked about in the presentation, and thanks to everyone for listening today.
Thank you, Mark. Thank you for a very relevant presentation that does take you on from the type of stuff that John was talking about earlier on AI and to the third talk in our session we'll be having after the tea break. We have time for questions. There's a few questions already in there. The first one is from Tomas Pialucha. Tomas, would you like to ask your question directly?
Yeah, but I think that, yes, the question was quite obvious to start with, but Mark gave such an excellent explanation in the second part that actually just I find it like outdated. But this is its question. Original question was just that all this analysis is heavily depending on the distribution type, and the question is the fundamental question which you actually dug very deeply into, is to gain confidence which distribution you are actually going to use for specific area under inspection. And this is just, I think that this is a fundamental work which needs to be done to make sure that this distribution actually applying this harness of the mathematics is actually fitting the reality rather than living in the world of fantasy.
Absolutely, and I think that's also where you're less restricted when it comes to using the full wall thickness distribution compared to like an extreme value approach. But I think it's also worth saying though that the sort of corrosion processes typically are restricted to a fairly small number of distributions. So typically what you would see would be an exponential distribution of wall loss, Weibull distribution, gamma distribution, for instance, would be the three, I guess the three main distributions that you would typically see in actual corrosion data collected in the field.
Fantastic. Mark, I will contact you later. I would like to learn more from you if it's possible.
Oh, that's
Thank
great.
You very much. Thank you very much.
Thomas.
Thank you.
Hi. We have a question, or a couple of questions really from Siga Terpstra, which I'll just comment on. Mark, from Siga, for certain corrosion damage mechanisms to be suitable for sampling, fit of distributions, homogeneous, large enough sample, can that be linked to certain corrosion mechanisms or conditions being inherently suitable, in brackets, having a suitable behavior most of the time? Would it help to create large databases to learn how mechanisms behave towards sampling?
Yes, I mean, I think, sorry, Martin, there's some echo. Yeah, I mean, I think much of the work that's been done to date has been based on what you actually see when when you get the data, and there's a lot of situations where there's some commonality in terms of what you're seeing, and the conditions may have been similar. And I think there's a huge potential for collation of some of this kind of information that many of the operators, the data that many of the operators have, and significant benefit from that, in the sense that you could start to use that to better plan inspections, and secondly to develop real world corrosion models, let's say, based on actual field data, which could be kind of key to doing better predictive analytics, I think. So I think that that would certainly be something there's a lot of scope for.
Great, thanks. Siga, did that answer the question, or did you have any other points there?
No, thanks very much. It is, maybe asking for the Holy Grail. We all know, if we are not so certain about do we see the distribution developing, then we have to inspect more. But if you are limited in inspecting more and more towards the 100%, when do you know that you can stop and trust the data? And then the question becomes, is industry experience having, let's say, a lot of that information in it, if you would pool that information? And could we become stronger by pooling all these experiences together and related to the corrosion mechanisms?
I think so. And I mean, I think especially with corrosion mapping systems, obviously for internal corrosion, and also laser data for external corrosion, becoming very widely available at at much lower cost. The amount of data that's becoming available to support that is increasing, I guess, exponentially. So the opportunity is certainly there to do something like that. And it's data you can learn from, fundamentally.
Yeah. Thanks, Mark.
Thanks, Egan. A couple more questions. One from Michael Smith. How would statistical analysis be used for local corrosion damage mechanisms?
I guess you're talking about, local corrosion damage mechanisms with things like fairly fine pitting and so on. I mean,
or even things like MIC. Or,
your
sort of thing.
Your demonstration appears to be about general corrosion, right? So I could see where statistical analysis would be very helpful for large areas of general corrosion. But when you have something like MIC, right, where it's very, very localized, it seems to me that the statistical analysis wouldn't be suitable for that. But I'm curious, is there ways that it can be used for predicting local corrosion?
I mean, if the corrosion is so local, as in you got very small diameter individual features and very steep sided, to the extent that you can't get a reasonable measurement with corrosion mapping, then you would use an extreme value type approach with perhaps a different technique, for instance, time of flight diffraction, just to establish the minima. but if the extent of those individual features are reasonable, then you can actually apply a wall thickness distribution type approach. So it's a case of looking at the individual data, and I think it's been applied to situations of quite, the wall thickness distributions are applicable in cases of quite localized damage, as in small diameter, relatively small diameter individual features.
Another question, a similar vein from Chris Moss. Some corrosion mechanisms, e.g. SEC and MIC, have greater variability than others, e.g. general corrosion. This presents a challenge to prediction. Does the statistical model cater for this?
I mean, I think from a statistical perspective, I can only really comment on it more from a what does the data show you, rather than a prediction element, and the data for some of those localized mechanisms is quite regular statistically. Yes, your total density may be quite low because you've got small individual features and they might be quite dispersed, but there's still inherently irregular statistical behavior associated with the distribution. So yes, there may be situations where there's simply not a good, the behavior at a sort of phenomenological level, if you like, is such that it's not going to, it's not random in the statistical sense, and that you would see that in the wall thickness distribution. And in fact, the recommended practice does give some guidelines on situations in which you shouldn't be using statistical analysis, and those kind of things where you may have like a heavy tail distribution are situations where you wouldn't want to, but it's inappropriate to apply these analysis methods.
Could you see like a double peak in the distribution in that case if you had some areas with MIC and some with general corrosion? Yeah,
there are cases where you can identify like a bimodal kind of tail distribution, but so that that would suggest two different mechanisms, as you say, but equally cases where the behavior just isn't kind of regular.
Okay, perfect. I've seen a quick hand went up from Andres from Equinor. Andres Rivera, quick question.
Yes, hello, Mark. Quick question. Hi. Are you aware of any ongoing effort or initiative from anyone to try to establish what is the best fit on the different probabilistic distributions linked to corrosion mechanisms? For example, those listed in 571. That's the first question.
Yeah. You want me to answer that first, Andres? You want to?
Yeah, and then I have a follow-up question regarding on the recommended practices. There are too many different damage mechanisms. Some that are very tricky, I will say, has been listed already: stress corrosion, cracking, and MIC. And we have, for example, mechanisms like naphthenic acid corrosions, where depending on the different process conditions, the damage morphologies can actually change from general, to very localized. Is that something that is included in the recommended practice today to be considered and evaluated?
Yeah, I'll answer the second one first, Andres. So in terms of mechanisms, yes, there certainly would be some mechanisms where there wouldn't be, I guess, enough confidence in terms of how you can approach it, and maybe variable, as you say, if conditions change, suddenly your distribution will change dramatically. But many mechanisms, in refineries, for instance, there are a range of acid corrosion mechanisms that do show regular statistical behavior, and the same goes for many of the sort of typical upstream corrosion mechanisms. But yeah, I mean, I think there's always going to be situations where you can't find something that's applicable. And then on the fitting of the distribution type. I mean, to some extent, it may make, sort of feels like it should make sense that yes, CO2 corrosion would typically be one distribution type, but I think certainly in my experience, you can, with CO2 mechanisms, assuming that the information you're given by the corrosion engineers is correct, where there's different CO2 mechanisms which will range from like a very exponential distribution, as in like literally a straight line on the log plot, to quite a heavy light-tailed sort of Weibull or gamma distribution. So yeah, there's variability certainly within one type of damage mechanism, obviously in different equipment items. But yeah,
Perfect. Okay.
it's certainly something worth exploring, I think. Yeah.
Thank you, Mark. Thank you again.